So today I'm going to talk about natural ventilation in a short road tunnel, and it's going to be an application or a case study using FDS and EVAC. And it's going to follow a similar arc as my colleague's presentation from yesterday, but we're going to go in a different direction and look at a different code and a much more transit-focused approach. So my day job is usually putting mechanical ventilation systems in tunnels. So road tunnels, rail tunnels, big enclosed stations, that's usually what we're doing. But this talk is going to be different. It's going to be about why that's not always the most appropriate choice for a given facility. So this case study arose from a project we did, and that project was an overbuild. There's a trend as highways are replaced in the US towards widening that highway to accommodate for greater traffic volumes and to also lower that highway. And what that buys you is the ability to basically cover that over with a slab. And what that really means is you've created new city blocks where there previously weren't any. So this is happening a lot in New York City right now. We have rail yards that are being covered over, which creates this kind of very unique problem with this very large space that you have to ventilate. So what happens when you cover over these highways? You get a very wide tunnel. It's potentially 6 lanes wide in each direction, right? Typically, we think of a tunnel, a 2-lane in each direction. So this is potentially 6 lanes in each direction, but it's also very short. It might only be 1,000 feet long. It's just a couple of city blocks. So as engineers, we need to analyze this facility and show that motorists are going to be safe in the event of a vehicle fire. And typically, what we do is turn to a mechanical ventilation system to do this, like the jet fans that I usually put into tunnels. But there's a bit of an issue when you think about such a short facility. Is it really necessary, right? As much fun as designing these systems is, it's not always the best idea, right? They're very expensive, both to install and to maintain. And you have to think about it. Taking it to the extreme, I can't go recommending that we put fans under every overpass just because someone called it a tunnel, right? I drove through a tunnel on the way down here that was basically just an overpass, but was a couple 100 feet long. Does someone call that a tunnel? Does it need ventilation? So here we're looking at how do you draw that line, right? So first, we're going to turn to the code, which is for covered roadways, NFPA 502. It's actually just a standard. But we find that emergency ventilation shall not be required in tunnels less than 3,280 feet in length, where it can be shown by an engineering analysis that the level of safety provided by a mechanical ventilation system is equaled or exceeded by enhancing the means of egress or the use of natural ventilation. So it's not forcing us to do a mechanical solution, right? It's giving us an out, but it's saying, look, it needs to be equivalent, right? And you need to show that it's just as safe as if you'd installed fans. The next question is, how do we show this quantitatively? NFPA 502 is written to be very vague and very broad on purpose. It wants to kind of give you some suggestions, but let you use your own engineering judgment. So we could say, lean on a survey of existing tunnels of similar length. Some will be naturally ventilated. Some will have mechanical ventilation. There's so many different parameters that go into deciding what type of system you should use, right? So we can't really lean on precedent set by existing facilities. And moreover, the authorities having jurisdiction, right? Those people who are going to actually approve the use of your design, they want a CFD analysis. They're not always sure what they want to see, but they want a CFD analysis with all the bells and whistles, all of the worst cases that they can possibly come up with. So we need to figure out a way to work that in rather than just saying, it's common sense, you wouldn't put fans here. So we go back to the code, figure out what the intent of the code actually is. So in all cases, the desired goal shall be to provide an evacuation path for motorists who are exiting from the tunnel and to facilitate firefighting operations. Okay, so to facilitate firefighting operations, we might do something like put a fire standpipe in the tunnel. Right, that's fairly straightforward. So we can say that the ventilation system needs to provide that evacuation path, right, and leave that up to the ventilation system to handle. And so what we're going to do is we're going to use tenable egress path criteria to make that equivalency claim, right, that mechanical ventilation can be equivalent to natural ventilation. So typically, what we might do is rely on a visibility of at least 10 meters to show tenability, right? That can be really hard, especially in large fire scenarios. So what we're going to rely on instead is the fractional effective dose, fractional irritant concentration method to do this. So we're going to track FED of toxic gases and thermal exposure, the FIC of toxic gases, and we'll set our criteria so that more susceptible occupants can still evacuate. So the toxic gas FED is going to come right out of EVAC. The thermal FED is a little bit more annoying to calculate. We're going to do it based on NFPA 502's NXB equations. So we'll output visibility and temperature profiles through the tunnel and then use this to calculate thermal FED for a theoretical occupant. So you'd pick your slowest occupant moving the longest distance, right? And you need visibility at the same time to slow down your theoretical occupant through patches of low visibility, right? They could be exposed to more higher temperatures then. So to be considered a passing result, we're going to set all of these less than 0.3, right? We're aiming for most people to be able to safely self-evacuate. Okay, so after all that set up, here's the case that we're actually looking at. We've got a fire vehicle near the exit portal. Traffic is stopped up behind that vehicle. This is typically the assumption we make. We have a 2% grade and an adverse wind. And what these are doing are basically forcing smoke over that stopped traffic. Right? We're looking for as much exposure to smoke as possible. That's also what the AHJ is going to be most interested in, is what is the worst of the worst of the worst. So we're going to look at a few different parameters and how they affect that equivalency between mechanical and natural ventilation. So we're going to look at two different fire types, dangerous goods vehicle fires versus heavy goods vehicle fires. We're going to look at the quantity of egress doors. So if we remember back to the code, one of the suggestions it gave us was that to maybe meet this equivalency, you can add extra egress doors. So we're going to look at how that changes the results. It's basically just shortening your overall egress path. We're going to look at two lengths of tunnels, 600 feet and 1,000 feet. And we're going to look at 2-lane versus 6-lane tunnels. So 2-lane is your more traditional tunnel. 6-lane is that widened highway scenario we talked about. So these are the heat release rate curves that we used. The dangerous goods vehicle fire grows at 20 megawatts a minute, and the heavy goods vehicle grows at 15 megawatts a minute. And that's from PyArc. The combustion reaction, we input that manually into FDS using emissions from an experimental vehicle fire. So they collected emission rates for all the asphyxiants and irritants already tracked. And what we do is we use the heat release rate measured in the experiment and then scale those emissions appropriately based on the heat release rate curves we just looked at. Okay, the results. So this table shows what it took to get that equivalency, right? What made a natural ventilation solution equivalent to a mechanical ventilation solution? Apologies for swapping units back and forth on everyone. The 600-foot length tunnel, 2-lane heavy goods vehicle fire, actually managed to pass with portal egress only. So what that meant was everybody could walk back to the entrance portal and be safe. But that same case failed with a dangerous goods vehicle fire. You needed to have additional doors, right? And that makes sense intuitively for us. Interestingly though, the 600-foot, 6-lane dangerous goods vehicle fire case passed with portal egress only, right? The tunnel volume clearly helped in some way there. The 2,000-foot cases needed additional egress doors to pass. Okay, so let's look at what that actually looks like. This is a visibility slice at 2.4 meters above the roadway. And this is for that 600-foot heavy goods vehicle fire case. And this slice is taken at about 300 seconds, which is when the last occupant is leaving the tunnel. And we see that visibility is down to 4 to 5 meters, which would have failed by that initial criteria of 10 meters if we'd gone that direction. But this case actually passed, and part of the reason for that too is when you look at the temperature profile. Temperatures, this is a section view, temperatures near the roadway are actually very tenable. It's warm, but not even remotely unbearably so. More interestingly, I think, is this dangerous goods vehicle fire case. So this slice is also taken at as last occupant exits. And visibility is down to 1 to 2 meters with some pockets of no visibility, which I think is, that's a lot. That's a lot for people to move through. But this case passed when you calculated FED and thermal FED. So we kind of said to ourselves, is that realistic? And there's actually a paper recently published by Purser where he suggests that occupants can move through visibilities of 2 meters for 20 to 60 minutes before incapacitation. And he's basing that on reports from fire incidents. So using actual data of how far people were able to move. And for the tunnels that we're looking at, right, they're very short. So even your slowest theoretical occupant is going to be able to evacuate in 5 to 10 minutes, right? So we're underneath Purser's suggested limits. I don't think we'd want to have a longer egress time. I don't think I'd be comfortable recommending that. But what it's suggesting is that, yeah, this approach is in line with what actually happens in tunnel fires. So what we can do is use this type of approach to form a basis for approval by the AHJ. You still have to take this to the AHJ and get their buy-in. They can always say no, they want something different, and in that case, you kind of have to comply. But you can use this to answer all the questions that they come up with. We've looked at taking this a step further, which I don't have a ton of time to go into, but you can look at how a suppression system affects the results. You know, how does that change the thermal environment? You can look at background vehicle emissions within the tunnel, right? How does that bump up your FEDs? Or you could take this and do like a construction phasing style approach, saying this intermediate case before we've got the ventilation system in is still tenable, right? And make a recommendation there. So we have used this, and I think it well backs up sort of the intuition that we have about, look, not every overpass, not every tunnel probably needs mechanical ventilation, right? You have to cut it off somewhere. And I think that's where we're going with this. And with that, any questions? Yeah.
Some questions for Katie?
She's very excited.
I'm always excited.
Very good.
I was born excited, and this is one of my fields. So very nice presentation, first of all. I have a question. Did you check the toxic level, I can't say that word, the toxicity level?
The FIC?
Yeah, exactly, but exactly in the areas for the visibility that drops near the dangerous good vehicle. Because when you're actually walking through smoke in person, it's almost unbearable.
Yeah, so we inspected FIC plots, which I didn't show here. And you're right, kind of near the fire area, it definitely is untenable. But because we're looking at a transient analysis, most people are out of the way. They're farther down the tunnel. We set criteria so that they moved when visibility was a certain level. And that's actually happens fairly quickly for people close to the fire. So yes, we did look.
I had a question. Sure. Did you model slowing of the occupants in the evacuation due to visibility?
Yes.
Okay.
One of my questions already have been asked, but I have a second one. Visibility is not a good quantity to refer to, because visibility is dependent on if you refer to an enlightened object or not enlightened object. It would be better to refer to optical density. What I ask myself, I don't know the paper from PERSA that you just showed there, but I think it's in the SFPE handbook where PERSA has this plot saying that with people come to a stop when they have visibility of around 2 meters, and they rather turn back instead of going forward. So I don't know how this both suits together, but maybe it's
that's a good thing to look further into. Thank you. The paper that he presented was just at the ISTSS conference in Sweden with RISE, I believe. But thank you. Yes, I'd like to look into that more.
Hi, thank you very much. I guess the slope of the tunnel was simulated by changing the gravity vector, but then my wonder is why the visibility at the end it lowers, because that's an effect you can see in a compartment, but in a tunnel that it's open and you have even like natural flow going out there. Yeah. Why was that like this?
I think it was just an artifact of the slice that I grabbed. I probably needed to pick a different slice there. I noticed that later as well.
Thank you for the presentation. I saw like a linear trend on your heat release rate curves. Can you please explain how did you get the data and how you use those?
Yep. So since we're looking at a transient basis as opposed to the steady state solutions we usually do, we assumed an inception phase of 2 minutes for the dangerous goods vehicle fire case. So it grows from, I think, to 2 megawatts in that early inception phase. And then we pick a constant heat release rate increase to model our fire. And that's based on some recommendations by PIARC, which is the World Road Association, I believe. So those curves are a small snapshot of what they recommend.
Other questions? I had one from an ignorant perspective. The heavy goods vehicle, what's a typical example of that?
A semi-truck.
Oh, okay.
Yeah.
And how would it compare these heat release rates to something like, I know we've seen that with new entirely electric vehicles like a Tesla, that they have a very different profile than a gasoline vehicle.
Yeah.
I assume that's still a lot less load than perhaps a large truck, but.
Yeah, good question. I'm actually the wrong person to ask. One of my coworkers just recently did a study on those alternative fuel vehicles, so I don't want to speak out of turn on that.
I just assume that's something everybody has to start considering as we move forward.
It is becoming a bit more of a topic that, and authorities want to know about it as well. They're starting to ask, how do I deal with this? How do I recognize the vehicle? You know, they're not always clearly labeled. So
Yeah, I just read an article about somebody was pulled over by a police officer for having a computer attached to their dash, but it was just their Tesla dashboard. So, any other questions?
Okay.
All right. Thank you again, Katie.
Thanks.